Hello, everyone. Welcome back to the AAS YouTube. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journals series. And I am super happy to have Bingjie Wang and Joel Leja with us today. Hello, Bingjie. Hello, Joel.
Hello.
Hello.
Cool. Bingjie, let's start with you. What's your geolocation?
I'm in the middle of Pennsylvania, State College, PA. I'm now a postdoc at the Penn State.
And just for, we'll put this in the description below the video, but I believe we did one in 2021.
Yes.
You were probably a grad student at that point. So.
Yes, I was still in Baltimore.
Yes, very cool. And Joel, how about you? What's your geolocation?
Yeah, also Penn State at State College, enjoying this wonderful Pennsylvania weather.
Cool. And let's talk about that. Summer's in full bloom. Does it get really humid in Pennsylvania? I mean, it's kind of East Coasty, so it might be humid.
Yeah, East Coast light, I think. It's not like DC or Boston, which is super soupy. Yep. But yeah, probably 85, 90 degrees, middling humidity.
Nice.
Yep. It's not so bad.
At least relative to me. So it is August 1, 2024 as we record this, and I'm in Phoenix, and we are definitely in our full summer. So yeah, it's quite warm. But we do get the monsoons rolling through, associated with dust storms, which are very interesting to see if you've never seen one. So they're kind of cool. Very good. Let's see. And Bingjie, what do you like to do for research?
Mostly I do a lot of modeling for those James Webb data. I've been focusing on the high redshift and also surprising discoveries, for example, the little red dots and the high redshift galaxies. I started focusing on the Uncover survey. So I have a paper on those discovery of the redshift 12 galaxies.
Yes.
And now I sort of shifted focus to those very strange red things, which we will be talking about today.
Very cool. And Joel, what do you like to do for research?
Yeah, I think a lot about how galaxies came to be in a very broad sense, usually. Thinking about how the galaxy population evolves from high redshift to low redshift, and doing a lot of interpreting imaging and spectra to do that.
Cool. Very nice. And that is going to bring us to this very awesome APJ letter. So first of all, note it's 19 pages, people, and it's a letter. So if you've got a great result, you can go more than standard letter. It is open access. It's the open access era. And so you can go grab a copy for free. Go get one. And RUBIES, evolved stellar populations with extended formation histories at Z between 7 and 8 in candidate massive galaxies identified with JWST NIRSpec. And Bingjie and Joel, take us away.
Cool. Yeah, so I think this is a really exciting story, and there's a bit of a precursor to these objects as well. So we'll dive into that. But this was an article we prepared on the first generation of the RUBIES survey, the RUBIES data, PI onto the graph. And so most of our co-authors here are the lovely RUBIES team and some friends. Yeah. Co-PI Gabe Brammer, a data wizard. And so the RUBIES survey was designed specifically to take the spectra of some of the surprising things that popped up in the James Webb imaging when James Webb first turned on. So luckily for us, there were many surprises in these images. And RUBIES, the goal of RUBIES was to particularly take spectra of very red things, which we anticipate will be at high redshift. And yeah, I think this was the first paper using this maybe half of the RUBIES survey. Okay. And so I'll tell a bit of the history here because it's quite relevant and interesting. And then Bingjie, who is the star of the show, will take over for the analysis. But yeah, so when Webb first went up and turned on, the surprises really started rolling in. And maybe certainly the most surprising and interesting to me have been these little red dots, as they've been known as. So they popped up in some of the very early release data in Sears and in other places.
Yes. Cool.
And they stand out because they're very compact. They're quite bright, and they're extremely red. Yeah. So if you go through the first images, they really stand out.
Let's take a look at this, what a small red dot looks like. There we go, rubies.
Perfect. Yep. Yeah. So these are the rubies in question. And they've been very fascinating from the very beginning. If you plot them in color space, they're major standouts. They're extremely red.
Mm-hmm.
Yep, and exactly. The y-axis being kind of a measurement of continuum shape or maybe spectral breaks. And what stood out about these little red dots initially was that taken at face value from the photometry only,
Yes.
it seemed that you could see two spectral breaks, a Lyman break and a Balmer break.
That one's interesting.
Yes, yes, indeed. Not something you expect to see because the other thing that became pretty apparent, these things are at redshift 7, 8, 9, and they're very bright. Yeah, so
Something turned on early.
yes, definitely. This created quite a bit of buzz. We initially figured they're galaxies. We had a little bit of evidence that there's other explanations for the red colors. You could have very bright emission lines.
Yeah.
Hey, but the placement of the photometric filters suggested for at least some of these, it wasn't necessarily a bright emission line, but probably more of this spectral break.
Yeah. Okay.
But hard to say, hard to say. It was tantalizing. If you think they're galaxies, if you say, okay, these are galaxies in the early universe,
Okay.
you open Pandora's box and it gets a little uncomfortable. You start measuring things like 100 billion solar masses of stars. They shouldn't form this early.
By standard models. By standard models.
By standard models, yes, very important. I think they are. I should say at the outset, galaxy formation has many little gremlins that can be tweaked to explain this without changing things like how fast dark matter halos grow or if there are dark matter halos.
Sure.
So there's many explanations. They're probably galaxy formation related. Yeah, these in photometry, these created a huge stir, and they were really exciting. I would say some of the most exciting times I've ever had as an astronomer, because
Cool.
they're so mysterious and they don't fit comfortably in any of our models. Right, so we initially had a very fast study saying if they're galaxies, they're very surprising galaxies.
Prizes are good, right? Mysteries are good.
Prizes are
They're exciting.
Yeah. Of course, there are other explanations just from photometry, and one that quickly became apparent, had to be true at some level, was that they could also be AGN, galactic nuclei, creating black holes. So they're point sources, effectively, almost. They're not quite point sources. They're actually resolved at blue wavelength, but they look pretty small. They're very bright. And so these could be dusty quasars, very dusty supermassive black holes. From photometry, it's hard to tell the difference. So originally we had 7 little red dots, remarkably common just from the first web imaging. I mean, Webb has this tiny field of view. So you find 7, it suggests their number density is very high, and that's a key part of the argument.
Yeah.
Not only are they massive, they're weirdly common. But are they black holes or are they galaxies? Of this original 7, we did have a spectrum taken pretty early on for one of them.
Oh.
And this would reveal, importantly, what are they? And the first one we got a spectrum for, broadline AGN at a considerably lower redshift. You can see this very broad H alpha. So 1 out of 7, definitely an AGN.
Okay.
Because there's still 6 more. And so, because they're so common, they popped up in many other surveys too. In Uncover, we already mentioned Sears, in all sorts of GRISM surveys and wide area surveys, like Cosmos Web. And so it became apparent that this is a pretty common type of object, and they're typically characterized by these broad emission lines when you get spectra of them. They're broad emission lines
Okay.
suggesting that it's a population of dust-obscured AGN.
Okay. Okay.
So that's kind of where we were before we got these RUBIES data. We thought, okay, they're probably not galaxies. They're probably mostly AGN. They're still shocking as AGN because they seem to be very, very massive. Hundreds of millions or billions of solar masses at very early times. Super remarkable. But we walked into this project expecting, well, we'll get spectra of these massive galaxies. We'll find out that they're truly AGN, mystery solved, and now we're going to learn all about these crazy AGN in the early universe.
Yes.
Hey, that's the plan.
Plans are good, but
well, we took the first spectra, and indeed, many of these red objects have broad lines, suggesting they are broadline AGN.
Okay.
But just because there are black holes doesn't mean there are also not stars. There can be plenty of stars and black holes. In fact, we expect them to coexist.
Sure.
And we noticed that the continuum of these objects has a very prominent break, which we normally associate with old stars.
Balmer.
So, yep, Balmer break.
Yep.
So we confirmed these are redshift 7-8 objects. They have these big, bright emission lines, and they have these characteristic spectral breaks of old stars, 100, 200, 300 million years old. And so the question became, and the goal of this paper, and what Bingjie will tell you about, is, all right, there are black holes, there are old stars, probably. There's some interpretation of the break. We're pretty confident they're Balmer breaks, but anyway. So is the continuum coming from old stars, or is it coming from a black hole accretion disk?
Right.
If it's old stars, these things have about the same masses as we thought originally. They're 10 to the 11 solar masses each. But if it's from a black hole accretion disk, then they're much smaller. And so that's kind of the goal of the paper. And that's something Bingjie is now an expert at analyzing and thinking about. So yeah, I'll kick it over to her.
So star of the paper, should we go to figure 3?
Great. Yes, we can go to figure 3 just to see the full spectrum first, and we can come back later.
And I'll get there. And figure 3. Okay, so what I'm going to do is zoom out so we get the global picture, and we'll zoom in as need be.
Yeah, the 3 spectrum looks about the same. We can just look at one of those. You can see the broad H alpha. We can just focus on the total model spectrum or the observed ones in gray. The broad H alpha is really hard to miss.
Yeah.
So that's strong indication of AGN activity, at least sort of dominating the continuous potential possibility. And the other, as Joel mentioned, is this break in the middle. It's right at the Balmer limit. So this figure does not show this super clearly. We can go back to figure 2 to see a zooming of this break.
Okay, question. Say a little something about what you mean by maximal, medium, and minimal. What is being maximalized, minimized?
Yes. Maybe that will become clear why we're doing this if we go back to figure 2 first.
Okay.
I will explain why we're doing this complicated modeling.
Okay. Let's go to figure 2 and Balmer break.
Yeah, so you see on the left corner, left part, we want to establish the or confirm this break is indeed a Balmer break. So what we did is to take an average of the observed spectrum. That is shown in black. You see they all have the same shape and break at the expected wavelengths, that is the Balmer limit. And more importantly, we can overplot the model average, that is from the average of 3 best fit galaxy model spectrum.
Okay.
You see they overlap on top of the observed average, meaning the models are also properly interpreting the break as a Balmer break.
Okay.
This is strong evidence that we are seeing light from stars, at least at this wavelength.
Okay.
But the other part of piece of the puzzle is, of course, if you see to the right, we see broad lines. This is the decomposition on the median resolution spectrum. The broad H beta is pretty unambiguous.
Okay, I'm with you.
So we have this coexistence of broad Balmer lines indicative of AGN, light dominating the continuum, and the Balmer breaks indicative of starlight.
Yes.
The question is, how do we interpret all of this? And that would lead us to figure 3. We approach this by 3 models.
Okay.
So if you go to this, will answer your previous question on what's the maximum, median, and the minimum stellar models are.
Gotcha. Okay.
Yes. So from top to bottom, we have the maximum, median, and the minimum stellar model. This is just I developed 3 priors to basically change the fraction contribution of AGN to starlight at the red continuum.
Gotcha.
So to let the data to be informed and be directed in different ways. All those models produce statistically acceptable solutions, but yield very different interpretations. I think we can start with the first one being the maximum stellar model.
Okay.
You can essentially take this as a galaxy fit. We only see galaxy model. That's in blue. This is a galaxy continuum.
Okay. Okay, I'm with you.
Yeah. So you see the fit is very nice. We produce a Balmer break and a continuous shape. And the remarkable thing is informed formation history. You can see it's on the right of the spectrum. So on the x-axis is age of the universe. On the top, I'm also plotting the corresponding redshift. You see under this pure stellar interpretation, the formation history is very early and rapid. The galaxies forming stars like at redshift above 10. So at face value, this would imply we'll form a lot of stars at a very fast pace.
Right. Okay.
Well, this is exciting. The way I really like this interpretation is that this is the simplest way, modeling-wise, to produce the observed break. We do not need other ingredients to reproduce the data.
Cool.
And the other is if you go to, I think, figure 4 or something, I will come back to the median model.
Okay.
So we can just interpret this next model first.
Figure 3 and figure 4. There we go, rest frame.
Sorry, figure 5 is a star formation history.
All good. Figure 5.
Sorry.
All good. Okay, here we go, figure 5.
Yes, figure 5. So this tries to connect, give some physical interpretations of what this maximum stellar model means. I guess a little bit background is another discovery from Webb is those maximally old quiescent galaxies we found at redshift 3 to 5.
Yes.
You can see one. I'm showing 3 galaxies. We can just focus on the black curve here. This is from a quiescent galaxy, also from the RUBIES survey. That is at redshift 4.9 with a stellar mass of 10 to the 11th. This is very massive and quenched at pretty high redshift.
Okay.
So if they form so many stars and quench so fast, that would mean they in the early universe they should produce a lot of observable light.
Yes.
We found those massive quiescent galaxies, but we haven't found their progenitors. There is some missing link between how they evolved into those quiescent galaxies we observe today. And now, if we overplot the inferred star formation history from the maximum stellar model that is shown in red, you see only the pure stellar interpretation can produce sufficient star formation to match those quiescent galaxies discovered at lower redshift.
Cool. Very cool.
In other words, this is a very elegant interpretation in the sense that we found progenitors of those maximally old quiescent galaxies.
Beautiful, beautiful. Okay.
Of course, there are uncomfortable problems. I'm not sure if Joe wants to list the different problems we encounter here.
Mm-hmm.
Yeah, well, I think the joy and the mystery and the intrigue of little red dots is that none of the explanations are clean, and all of them have their own issues, and so we tried to really present a balanced view in the sense that all of the explanations so far are incomplete. The most straightforward is that we have these broad lines, but it doesn't matter. All the continuum we're seeing is from stars, and we get these very massive galaxies. They connect nicely with massive quiescent galaxies at lower redshift. But they have very high stellar masses, and they form very early. And so if you try to place these massive galaxies into a dark matter halo, using a number density argument, we have this many massive halos, we have this many galaxies, with the number density on the little red dot or galaxy side being very rough. You find the stellar mass is very high compared to the halo mass. I think we have a figure for this. Is it figure 6 or 7, Bingjie?
Yeah, 6 or 7. 6 is the observational evidence, and 7 is the theoretical comparison.
Right.
Yeah.
Okay.
We can pause here too, because this is, I think, one of the other challenges with the maximal stellar model. This is these plots are kind of funny to read, but the central figure is a good one to focus on. So it's cumulative stellar mass density. So how much stellar mass is in these objects as a fraction of the total stellar mass in the universe?
Yes. Okay.
And so the pre-Webb expectations are in blue.
Okay.
And we have 2 of our objects at redshift 7. And so in the upper right, those 2 little stars there,
Yes.
their position relative to the pre-Webb mass function, hey, they're about equal on the y-axis.
Yeah.
There is as much mass density in these 2 objects as there is in every redshift 7 galaxy detected ever pre-Webb. So if you add up all the galaxies we've seen before, their mass density equals that in these 2 objects at redshift 7.
Wow.
Right?
Wow.
It gives you some pause.
Indeed.
And it's at redshift 8, it's not quite so bad, I think. We only have 1 object at redshift 8, so maybe only half the stellar mass density
Still
is little red dots.
Still. Wow. Okay.
And I want to draw some attention to the uncertainties, which are more than an order of magnitude, before taking into account the fact that we can't really measure the masses. So this is our best guess. It's not very precise.
Okay.
We'll talk about how to make it precise at the end, maybe.
Yeah, we're going to come back to that for sure. Okay.
And I'll just touch on the other problem. If you scroll to figure 8 quickly, well, this isn't a problem. This is exciting. But sorry, figure 7. Yep, this is the one.
You want 8 or 7?
I apologize. Figure 7. That's the one.
All good.
Yeah.
All good.
And the third panel from the left is maybe the one to focus on. So if you take these galaxies, you interpret them as all galaxy, all starlight. The continuum is all stars. We get these stellar masses. We get a number density. We link that to the underlying halo.
Yeah.
We use abundance matching. We put these galaxies where we expect to be in the halo mass function, which is well understood because halos only act through gravity. So this is what you do. And then in the upper right, these are the Well, in the gray area is the no-no zone.
Yeah, I mean, yeah, more stars appearing. Yes, yes.
That's not a good place to be. That's if you take the halos of the mass that we expect them to have. So you take the dark matter halo mass and you multiply it by the cosmic baryon fraction.
Okay.
So how many baryons do we expect to live in this halo as a whole? That includes all the gas, all the stars, everything. Assume all the gas is equal to the cosmic baryon fraction and it's all turned into stars. That's the purple line. If you're above that line, you're in a really weird place where you need to have more baryons than dark matter proportionally.
Yeah.
And it all needs to be stars.
Yeah, which is weird. Okay.
Not how we think things work. There's usually a lot more feedback. You can only turn maybe tens of percent of your baryons into stars if you're lucky.
Yeah.
So the maximum stellar mass solution implies that that number is around 100%-ish. There's two sets of points here, which correspond to the uncertainty in the actual number density of these things.
Okay.
I think the formal calculation is in black, but we think the field that we targeted originally is overdense with these objects, and so a more reasonable estimate's in gray. They're both near the purple line, but
Yes.
that's what we're showing.
Mhm.
So, this would imply extremely efficient star formation in a mode that we've never seen before, and maybe a healthy dose of errors as well, in a few directions. That's the maximal stellar mass model.
Yeah. Cool. All right. I'm with you. Mhm.
Yes, I guess the other point is those are very compact. It's like 100 parsec in size.
Yeah.
It's very hard to imagine to put so many stars into 100 parsec. So
For one.
while it provides a very elegant connection to the maximally old galaxies we found, there are lots of problems with this pure stellar interpretation.
Yeah.
The other side of the coin, of course, they are low mass galaxies with bright AGNs.
Yes.
So I think we can go back to figure 3. I can explain what I did for the medium stellar model.
Yes. Okay. Hold on 1 sec. Slide figure 4, figure 3, and let's go to up on A where we were, and let's go minimal. Yeah. Okay.
Yeah.
Mhm.
So the median, we can just look at the middle panel.
Mhm.
Basically, I just impose sort of a prior to have this equal or a larger AGN contribution to the red continuum. So
Okay.
you can see in this model, instead of starlight, we explain the red continuum as a highly reddened AGN, and that is the red curve you see.
Yes. Mhm.
And of course, if we have AGN dominating the red, it naturally brings down the stellar mass.
Mhm.
So we do not have this too many stars forming too fast problem.
Issue. Okay.
You can also see from the formation history that's also to the right, the star formation rate decreases significantly. Also, we still see this decrease in the most recent time to produce the observed Balmer break. But overall, we do not expect significant formation above redshift 10 or something.
Yeah. Okay.
So that's our median model.
Okay.
The minimum model is I try to inform model that there are more AGN contributing the light at the red continuum.
Mhm.
I should have emphasized that this model does not really replicate the observed break strength. So it's more of an illustrative case that we show how constraining the data is, or like the lower limit we can derive on the formation history.
Yeah. Okay.
So I will focus on the median stellar model here.
Okay.
This has a few advantages. You can see clearly from here, we have stars dominating the UV, that is shown as those blue curve, and AGN dominating the red.
Mm-hmm.
This is consistent with the broad lines, as you can also clearly see here. So where we have broad lines, we have AGN dominating the light. So that's a natural explanation. And also, we see this apparent wavelength appendance morphology. So we measure the size in the rest UV and also the size in the rest optical, that is the red part.
Okay.
And we find in the red, they are unresolved, but they are sort of resolved in the UV. So this is also consistent with this interpretation that we have a transition from the starlight to the AGN light.
Okay.
However, a critical weakness here is, you see the AGN and the Galaxy have to conspire to produce the observer break.
Ooh, magic. Okay.
Yeah, so the AGN just have to peak out at the right wavelengths with the right strength to
Magic.
produce the observed spectral break.
Yeah.
I mean, it can work if we just observe a few of them, but as we see more and more, it's pretty common. So it becomes increasingly difficult to explain the observer break with this joint AGN and Galaxy model.
Yeah. Okay. Good.
Yeah. Well, with that being said, if we put this into contact with, say, the local stellar mass, black hole mass relation, I think that's what we show in the later figures. We see this median model actually predicts stellar mass and black hole mass relation that's in less tension or requiring few mergers to become consistent with the local scaling relations.
Okay. Okay.
Yeah, this is figure 8. If people want to look at it.
Yeah.
Okay.
Let's go down there. Yeah, I knew that was the last one. Sorry. 5, 6, 7, 8. Here we go. There we go.
Yeah, that's where we plot the black hole mass and the stellar mass for those 3 models. And also in gray is the local scaling loss. You can see in the median model, it's closer to the local elliptical scaling relations.
Median and max. Yes. Closer.
Yes.
Still
so that's basically all the modeling approaches we have tried. This is done to let the data to inform the different pieces as best as possible. Nice. And we try to tie those different pieces together, but in the end, just looks like none of the pieces really fit into our conventional understanding of galaxy formation and cosmological models.
Yeah, very good. Very good.
Yeah, I think this is where the discussion sort of ends in the paper. I'm not sure if Joe has anything else to add.
Yeah, I think there's one last figure that we can focus on briefly, and then we can discuss what it all means. So figure 4, I believe, and this one's a bit of a thinker, so I can walk you through it.
Wavelength, yep.
Yep. Yeah, so this is the y-axis is the equivalent width of the H-alpha line. Okay. How much flux is in H-alpha relative to the continuum. And we've plotted here a bunch of gray points that are lower redshift, little red dots. And then we have some red points and some black points, which are the 2 objects in our sample where that we put on this plot. And what this is showing is effectively, it's kind of the ionizing photon budget in an AGN, in an active galactic nucleus. And that's kind of related to the shape of the spectrum of the accretion disk. Yeah. So how many ionizing photons does it create per photon at H-alpha wavelengths? Okay. So how steep can AGN get? Normally, for a normal AGN we see in the nearby universe, the highest, the steepest, the bluest you can make it will produce H-alpha equivalent widths of a few hundred angstroms. Yeah, okay. Little red dots all seem to blast right past that limit. So if they're AGN, they're weird AGN. They're very blue AGN. And this is one of the other things that is uncomfortable about the higher stellar mass model, is that if we increase the amount of stars, we decrease the amount of AGN continuum at H-alpha. And so we're effectively forcing the AGN to be bluer and bluer and bluer to produce these very high equivalent width broad lines. Right. So if you had no stars at all, we're just looking at a bare AGN, right. And the maximal stellar model is true or something close to it, we might actually find AGN equivalent widths of 1,000, 10,000, a few thousand. And no AGN we know of produces these. Right. And even at face value, even assuming there is no galaxy continuum, we're still outside the realm of normal AGN.
Indeed. Okay.
So
Okay.
what do we do about this? Yeah, and then we can maybe spend a couple minutes wrapping it up. I'll give you what I think, and Bingjie should weigh in too. But yeah, I think where this leaves us here is that the maximal stellar model, the minimum stellar model, and the medium stellar model, they're all inconsistent with our expectations.
Right.
Either we have these massive galaxies forming very early and very efficiently, which means we have a lot of work to do on the theoretical side to
Correct.
explain if this is possible. I mean, where's the feedback?
Right.
Where's the gas being blown out? What are all the processes that slow this down at low redshift? They're not working here, if that's correct. Or we have these low mass objects with this sort of a bit of a conspiracy. A break has to be in just the right place. They have to have just this very red spectrum. And these black holes that we're assuming are there don't really seem to work like normal black holes. They're different in ways that are very confusing. They're normally surrounded by these cocoons of hot dust that are bright in the mid-infrared. We don't see that. They're normally blasting out huge amounts of X-rays. We don't see that. They normally put out only so many ionizing photons, resulting in this empirical ceiling on the emission line equivalent widths.
Yes.
These objects seem to be well above that.
Yeah.
And we see these signatures of old stars at 3,500 angstroms rest. So that really suggests they're sort of intermixed with the stars. You're sort of seeing both stars and black holes. Something is making both of them be sort of approximately luminous, and that's a bit weird. Why would it's nicer to have one explanation for something weird you find in the universe instead of invoking two weird things.
Absolutely.
So yeah, either way we go, it's somewhere new, and this is awesome. It's really exciting. But which way to go? Which one is more likely? The low mass galaxies with the way overmassive black holes, or the really uncomfortably massive galaxies that maybe also host black holes, probably of lower mass. I should mention we didn't mention how we estimate the masses, but it's an empirical relationship built at low redshift using the luminosity and the width of H alpha.
Yes. Yes. Uh-huh.
It probably doesn't work very well here. We know these are different AGN than normal.
Right.
Yeah, the AGN masses also need a huge grain of salt. So yeah, no matter how you slice it, there's parts of the story that we don't understand yet, and that's awesome. That's exactly why we build web.
We're gonna we're gonna come back to that point. Very good. Bingjie, you want to say anything? You want to go?
I think Joe summarized this pretty nicely. And also this is why, as a modeler myself, I'm so excited about those little red dots, because we need something new, something fundamentally new to explain those things.
Yeah, very cool. Very nice. Very nice. Beautiful piece of work. Beautiful piece of work. And I want to say, well, congratulations on your discovery of the polymer breaks with these emissions. Very cool. Very nice. And as you note, it raises more questions than it answers. So yeah. So let's go there a little bit. Where do you think we go from here? Given the published article, what is it you think we need to disentangle or shed a little bit more light on this mystery now that we have a number of uncomfortable things or some pretty amazing coincidences going on? So where do we go from here?
I think the obvious next step is to ask for more data. I know we ask for more data, we get the spectrum, and only led to more puzzles. But more data can potentially help is first, if we have deeper spectrum to reveal possible stellar absorption features.
Yeah, okay.
This would really confirm the stellar origin of those lights.
Yes.
Or we can go to longer wavelengths.
Okay.
Where those infrared bump from stellar light or the light from a dusty torus would give us different expectations. So that may also shine light on the nature of these things.
Okay. Cool.
And the other part of course is just we may just need some stroke of genius to add some new model pieces to, and then all of a sudden all things would make sense.
Call the theorists, do something. Very cool. Very nice. I love it. I love it. Great discovery, great mysteries to solve. Very cool. And I really look forward to seeing, this field I think is going to evolve rapidly over the next couple of years, and it'll be really exciting to disentangle this a little bit more. So very cool.
Yeah, and I think we have our own ideas about what's going on in these objects. We think it's some combination of black holes and stellar light. But they're not the only ideas in the literature. There's a wide range of theories out there for what these little red dots can be. Ranging from low spin black holes to dusty outflows powered by AGN to other pure stellar interpretations, and the door is kind of wide open. It's sort of an awesome time to
Twist
to
your
be
IMF.
thinking these
Yeah.
things. There's a lot of possibilities.
Yeah.
So and if they are pure stars, as Bingjie mentioned earlier, their sizes seem to be something like 100 parsecs. So you take the Milky Way, you double or triple the number of stars, and then you compress the size by a factor of 80. That's what they, at face value, that's what they would be.
Yeah, that answers really more questions. Or more questions. Very good. Very good.
Anyway.
Bingjie, Joel, I want to thank you so much for walking us through your very awesome article. Very nice. And that will do, everyone. And I hope this made your little red dot day a little bit better. And we will see you on the next one. Bye-bye.